something, just unmute yourself and let us know, okay? So we're trying to do it in hybrid format. So welcome everyone. This is the last day of the Quantum Week, which has been very exciting. And today is dedicated to quantum computing. I will talk a little bit about kind of what our activities are in this area, and then I'll introduce our wonderful keynote speakers, and then we'll have a panel at the end. Okay. So my name is Emelianenko. I'm a mathematics professor and also chair of the math department here. I've been involved with QSEC for 3 years now, learning a lot about quantum computing. Originally, my research is in computational mathematics, but classical computational mathematics, and now I'm doing a lot with quantum computing, very exciting area. I wanted just to start maybe with a show of hands. Who here has taken math classes in GMU? All right. Any math majors? 1, 2. Okay. How about physics? 2. Okay. Computer science. All right. Engineering. Okay. Anybody who is here not from the list that I mentioned? Any majors? Yes. Which major? Art major. Awesome. Wonderful. If you're interested in quantum computing, that's the way to go. Any other majors I didn't mention? Everybody was covered. Okay. So minor in engineering. Okay. So undergraduates or graduate students? How many undergraduates here? Okay. How about grad students? Okay. Postdocs? 1. All right. And I guess the rest are faculty or visitors, right? Okay, awesome. So we have a great mixture. So that you know, quantum computing at Mason has been rapidly developing, and we're building momentum. So this is a great time for you to get interested in this. I will not talk for too long because we have a lot of talks planned for you guys, but I wanted to just maybe briefly, if I can, tell you why this is so important, right? So I'm showing this just for those of you who know maybe a little bit about computing. Yes? Oh, thank you. I'm not following instructions. So there's this owl that picks up the noise, and if I stand too close, it might be bad for people. So, anybody heard about Moore's law? Okay, so basically this is what it says, right? So the Moore's law, Moore was the person who actually predicted the growth of the transistor technology back in '65, and so he was saying that the number of transistors on the computer chip should be doubling every 18 to 24 months. This is not the case anymore. So if you look at some of these graphs, it's slowing down. So what does it mean? There are limitations to how much classical computers can handle, right? So we have been experiencing a rapid growth, but it's not going to continue forever, right? So there are limitations in terms of when you go down to the quantum effects, then you can't really push it further. So the reason quantum computing area is so exciting is because it's offering ability to circumvent this issue and actually go further and go beyond what classical computing has been able to do, right? And this graph with all the data is just to say, like, data is all around us, and there are so many data intensive applications we cannot handle them. And some of these computational problems that some of the people you will hear from today will talk about would take years on a regular computer. So we need something better, right? So we need some technology. So a lot of people in this room have been thinking about it, and this is just the picture of IBM computer. It's not the greatest picture because you can't really see what's in it. So I really think that we should do like a field trip to IBM facility if they can show us. But so 20 years ago, it was just a dream. Now it's not a dream anymore. So you will hear from people today who actually work closely implementing algorithms on real machines, as well as thinking about what will happen in the near future. So you're here at a very good time, and hopefully you will learn by listening to people and their perspectives that there's a lot that you can do, right? As students, as people who are interested in these algorithms, you can learn and you can contribute. So it's not just something that has been, developed already. So this is a rapidly developed area. I will not talk about more things, but let me just mention one. In many projects that you will hear about today, and for the people who are in this room will tell you more the details, the premise is that when you're solving a problem, you can do it faster. But how much faster is the question? So some questions are actually, for instance, the Shor's algorithm, which is the prime factorization problem, can be exponentially faster on a quantum machine, right? So just imagine what exponential speed up means, and then maybe, you know, these two curves are not really doing justice to this, but you can really speed up the computation, which is extremely important in encryption technologies and RSA keys and things like that, which is why people are raving about this. But some other algorithms might still experience speed up, but not as significant. So it could be polynomial rather than exponential. So when you hear those words, this is basically what it means, right? And just to say, in our group, there are people who work on algorithms that have to do with a variety of different disciplines. So there are applications of these algorithms in scientific computing, in biology, in space, in artificial intelligence, in health. So you name it, right? There are so many different areas where you can apply them, but it comes with a challenging task of actually implementing them with a quantum machine. So a lot of different things to take in, but it's a very exciting area, right? Just to mention the members of the team, some of which are here. So myself, I'm from that. We also have Michael Jarrett, who just joined us, so he's in the back of the room. If you haven't heard him speak on Wednesday, he will be in the panel later today. He's a joint math and CS faculty who just joined Mason recently. Wei-Wen Zhang, he will give the keynote address today. He's from electrical engineering, electrical computer engineering department. Fei Li is from CS, Antoine looking at from math, and Nijin Qian from physics. We're growing, right? So there are a lot of, if you are from any of these departments, you have an opportunity to actually talk to faculty, but also just keep in mind that we're working closely together. So it's not like you have to only work with one person. Sometimes you have options to pursue joint projects, and we have a lot of partners. And I forgot to list mine, I apologize.
Won't forget you.
You see, so I'm not passing the test. All right. So for students specifically, I just wanted to highlight that I'm almost out of my time, but it has been extremely rewarding to work with students on joint projects, and we have some success stories here. Just wanted to highlight. Javier Ichiro, he just he's about to defend his PhD. He passed his pre-defense in CS, and he's been working with me in physics and myself in math on a project related to quantum computing. Got an offer from Microsoft. Really happy about it. Really great. Very happy for him. Ian Morris was a physics bachelor student here. Was working also in a joint project on supported by QSEC. He's now in PhD in Michigan State in physics department. John Kent is still our joint co-mentee between Anton and Michael in our program. Connor Mooney, who I believe presented yesterday on his research. He's a student. Is Connor here by any chance? I don't see him. So he's finishing bachelor degree here and going to UMD for grad school. And so we also have, so what I'm trying to pass, so Raphael is our undergraduate who's now a PhD program here as well. So we have a variety of different projects where people from all areas can contribute. So take an opportunity to learn about them. There are funding opportunities that QSEC has provided. This is just one project that I really feel is very exciting. This is something that me and I have been working on. This is optimization of trajectories of unmanned vehicles with quantum computing, and Dewey is working with us on that. But there are research positions during the summer. There are also positions for undergraduates to pursue summer research projects. You should definitely talk to Fangyu or Patrick. These are the people who distribute. So certainly try to think about what you can do, what your interests are. And this is just a partial list of things that we do, but if you're excited about certain area of application, there chances are you might have a faculty member here who already is interested, and you can become a mentee for the summer, check it out, and there are a lot of ways to contribute to these efforts. Okay, so just keep in mind that We are open to new students. We are building these programs. We are interested in curriculum development, and this is a good segue into a promotion for a course that Emelianenko is going to teach this fall. So this is a joint physics and math course that's called Introduction to Quantum Computation and Quantum Information. You can register. It's registration, I believe, is open already. And there's another new course that Michael Jarrett will teach on quantum algorithms that's also jointly run by Math and CS department, but everybody's welcome to register. So if you have questions about those courses, take a flyer for Ming's class, talk to Michael if you want to learn more about those topics classes. Any questions before I introduce our first speaker? So as I mentioned, we have a exciting program for you. We have 2 keynote addresses, and then we will have a fireside chat, which is like an informal panel where you'll be able to ask questions from the faculty working in this area. All right, so without further ado, oh yes. Where is it? Yeah. Where is the IBM machine?
You suggested
I hope.
New York.
Is it like upstate New York? Yeah. Well, there is the Ion Q, which is close by. Maybe they allow people to walk in and look, right?
Actually, Johns Hopkins has.
Yeah, so we should schedule a field trip.
Yeah. Yeah, they're yeah. Yeah, do you remember where they were?
Any other questions while the speaker is preparing?